Hey, John here. I'm looking at the data sheet for the Z80 CTC, which stands for Counter Timer Circuit, by the way. I've always called it the Counter Timer Controller. Crazy me. But there seems to be some confusion here with what this thing was really called. This data sheet, as you can see here, does closely resemble a facsimile of the 30-year-old hard copy that I still have lying around the old basement here, where you can clearly see the only real change was the logo up here that was removed and replaced with this beautiful modern version here. The old one, I guess they didn't have the rights or something to the trademark that looks always to me a lot like one of these 45 RPM records inserts, but whatever. Okay, the point is, this does look like an accurate representation of the last manual that I recall seeing on this chip, and with the one that I used for the coding and in the logic that went into the code we're going to talk about today. Now, there is another interesting side note that if you look at this data sheet, and then you look at the user manual that comes from the Zilog website, you'll notice that whoever was put in charge of this didn't see fit to even take the time to name the chip correctly. And as was often attributed to Einstein, this particular quote comes to mind. Anyone who doesn't take the truth seriously in small matters cannot be trusted in the large ones either. And he originally wrote this in German, so there's variations on the translation. But roughly speaking, that's what you see when people like to quote him in this context. So what am I getting at? Well, this data sheet is probably accurate and correct, while the modern user manual, if they didn't take matters of the small, it makes you question the rest of it, is what I'm getting at here. So you might need to make sure that you read the data sheet as well as this, if the user guide here is easier for you to read. The narrative in here is a little bit different than the data sheet. They give you some diagrams and things in here that, in my opinion, are not of much use for this particular discussion because there's a complete lack of detail here. And even the hard copy that I have from 30 years ago doesn't really do justice to the detail in here for us to really understand how to use this thing. So I'm going to draw my own. Let's start by having a look at the block diagram of what's inside Z80 CTC, or more accurately, what's in one single channel of the CTC. So there's 4 of these, right? CTC has 4 channels. Each one is exactly the same, and they all do this, okay? There is a little, it can do additional things, all right, but the modes that we care about and the functions we care about are summarized in this block diagram, okay? So here's where we're at. We can either operate in timer mode, which means we're going to be using this circuitry up here, or we're going to be operating in a counter mode using circuitry down here. Regardless of what mode we're in, we're using the circuitry over here to do the actual timing or counting, okay? So let's look at this and then look at the rest of that order. The main thing that happens is that there's what we call a down counter. And the way that works is every time there's a pulse that comes in on this signal over here, the value in this counter, which is an 8-bit value in the CTC design for the Z80, is decremented by 1. So if it's currently 7, and there's a pulse, it'll become 6. If there's another pulse, it goes down to 5, and so on. When it becomes 0, there's this over here will go high. This is the Z80 output. I like to call it that. When this thing goes high, the signal feeds back into this counter to tell it to reload itself so that on the next tick, it'll have the value that comes from the time constant register, which is also 8 bits long. Let's say that the frequency that comes into this down counter, this is the input that causes it to count down. Let's say it's 100 hertz. And let's say your time constant down here is 2. So if this thing is currently 0, it will have reloaded itself with a 2. All right. So this is going to come along at 100 times a second. Current value is 2. There's a pulse. It goes to 1. It's not 0, so this is low. It pulses again. This was a 1, it then becomes a 0. This thing goes to a 1 now. At that point, the 2 gets put back in here. This thing goes back low again. Next tick comes along. The 2 comes a 1. Next time it comes a 0. This goes high. It reloads itself with a 2. Next time it counts, it goes to a 1. Next time it counts, it goes to a 0. And this goes high, reloads, and it goes on and on and on, okay? What this will have the effect of doing is this 100 hertz coming in over here will look like 50 hertz coming out of here. So the frequency here divided by the time constant in here will equal the frequency coming out over there. So this whole thing allows you to divide the input to this counter by the time constant. That's really what we're looking at here, okay? So that's what this part of the circuit does. Now let's look at the part on the left. Let's ignore this down here and look at the what we call timer mode, okay? In timer mode, what we do is we connect one of these two up to the down counter. Let's assume we're going to use the divide by 16 mode. This is what we call the prescaler. Back in the day, or even today, you still see this a lot. You can bring in a high frequency here, like 10 megahertz was a high frequency in 1980. And the circuitry over here might not be able to run at 10 megahertz. So counter timer systems like this usually always had these prescalers. So by forcing you to divide it by 16 or 256 or something, all right, no matter what, you've got to divide it by at least 16. The rest of the circuitry over here only needs to run at 1/16th of the rate of the main system clock over here. Saves you money, okay? So usually the whole point of these things running in timer mode anyway is to generate a periodic pulse over here so you can measure the time of day or something. So if we were going to use this to measure, to meter out and get like a 1 kilohertz signal out of 10 megahertz, you need to divide that by a pretty big value. So you're usually, like my point is, you're usually dividing by big numbers anyway. And the down counter here has only got 8 bits in it. So if you divide by 256, and you can also divide by 256 again, that allows you to divide by 1024. And that'll let you take 10 megahertz all the way down to just under 10 kilohertz, okay? So, and that's the kind of thing you'd oftentimes want to do with this sort of a setup, all right? So, if you choose divide by 16, what you're then doing is you're just simply taking the system clock, which is usually referred to as phi, or an italicized phi symbol, I guess, and running 1/16th of that in here, dividing it by some additional value, and generating your output over there, okay? So that's what it means to be running in timer mode. What it means to run in counter mode is you go through this, okay? Let's ignore the synchronizer for a minute. And look what happens if we just look at this clock trigger input for this particular channel. If it just runs right into this counter, and logically, that's how I think of it when I program this. I'm going to get into this detail here because if you look at this on an oscilloscope, it'll jitter all over the place and you won't know why. And the answer is this, okay? Let's start by ignoring it. If we have, 100 hertz coming in here, divided by your time constant, if I put, 100 in here, every time this ticks 100 times, this will tick once, right? If the time constant's 100, the frequency is 100, we get 1 hertz coming out over here in counter mode, okay? So that's great, all right? Why would you want to use this instead of that? It depends on your application. In our application, for example, we need to generate the bit rate for the SIO. And we want to run the SIO at standard bit rates, like 56 KB or 9600 bits per second and stuff like that. And the SIO, remember, needs to have 16 times the bit rate being applied to the SIO. So if I want to run at, say, 9600 baud, or bits per second equals baud in RS-232, by the way, which is why people always use the wrong words. Everybody always says baud when they really mean bits per second. That's a whole nother discussion, but I'll use them interchangeably here because our baud rate and our bit rate are the same value in this application. So we're going to need to have 9600 times 16 coming out over here. All right. Now, you can't get that evenly. If you have 10 megahertz going in here and you divide it by either 16 or 256 divided by some other value, you cannot get 9600 times 16 to come out of here. It's going to be plus or minus some massive amount of error. So that's why I have another clock that runs at 1.84 some odd megahertz that comes in over here. Again, ignoring this, what happens is if you take the 1.84 some odd megahertz and you divide it by 1, in other words, you don't divide it at all, the value here would be 1.84 some odd megahertz, which is exactly equal to 115,200 bits per second times 16. Okay? That's why I chose that speed for this signal. This is what I call baud clock in the schematic. Okay, so if I then divide that by 2, but my time constant is at 2, again ignoring this, I get whatever 115,200 is divided by 2, which is 56 kb. If I divide it by 3 or 4 or 6, it turns out if I divide it by 6, I'll end up with 19,200 times 16. So I would run it at 19,200 baud, which is a very common bit rate, okay, a baud rate. So this will divide evenly provided we choose the baud clock input. That's a nice clean multiple. Even though it's a weird value, it evenly divides these bit rates. That's why I chose that other crystal, okay? So why is this here? What's this doing? If it all works great, if we just connect this up to the down counter. Well, there is some part of the problem with reality sets in, okay? So it turns out that in order to keep the timer running and doing all the other things that the timer has to do, the circuit, the CTC chip as a whole, the counter and all the interactions with this, that when the outputs go high and low, are to be synchronized to the main system clock up here. Okay? If they're not, you can run into real problems that are related to what we call metastability. And you can Google that and read about it. I could do another talk on that if anybody's interested in hearing about that. The bottom line is bad things can happen if the frequency or the pulses that arrive on this down counter are not synchronized to the edges on the phi clock. Okay, so we use this as a oversimplified conceptual synchronizer circuit. You'll see these if you ever do any work with FPGAs and stuff. You'll use a sequence of 2 or 3 latches like this in series to synchronize a signal to your system clock. Okay, so let's just keep this simple. This will work as well. It turns out the more of these you line up, the more you can overcome arcane, outrageous situations that in theory can arise. So this is a super simple synchronizer, all right? So the way this thing works is every time there's, let's say this is a leading edge, a triggered latch, okay? Every time there's a rising edge on phi, the value on this line is copied over here to Q1 and then sent into the down counter. So all this thing really does is it makes sure that no matter when this signal is going high and low and everything else, the signal here will only be able to go high or low when phi is on a rising edge, okay? Now, because of this, by the way, we need to make sure that the clock trigger input to the CTC is never more than half the frequency of phi. If you dig through the spec sheets, that's in there. Now, as you can see, here's the 10 megahertz CTC chip, 100 nanosecond minimum period for TCC, which is phi, right? The master system clock cycle time, right? So 100 nanos there. And down here we have the clock trigger cycle time, which must be at least 2 times TCC. So this is the minimum column, right? Which is the highest frequency, right? Because we're dealing with period here as opposed to frequency. So let's look and see what the impact of the synchronizer has then on what's going on. So if this is phi, our main system clock at whatever frequency it's running at, and let's say we have another frequency in here that is less than half of phi. Arguably, this is a little bit less than half of phi, all right? What comes out of that latch? Well, what comes out of the latch is whatever's going into it on every leading edge of phi. So on this leading edge here, the clock trigger input, which is what this guy is low. Therefore, the output of that latch, I marked as Q1 in the drawing, is low. The next time it looks is on this rising edge here. It sees a high. That then goes high here. Stays high. It's got another rising edge of phi. We see a low. It goes back down here. Rising edge here. It sees a high. It goes up. Rising edge here. It sees a low. It goes down. Rising edge. It sees maybe a high. Maybe this is just a little bit before that one. So, okay, great. It's high. All right. Rising edge here. It's high. It stays high. All right. And this is what we're going to see is the jitter we're going to see in a minute. The next rising edge here is low, so it goes back low. Rising edge here is high, on a high level here, so it goes high. Rising edge, it's low, it goes back down. Rising edge high, we go high. Rising edge on a low, it's low, and so on. So what you see here is the same number of pulses over the course of time that we see up here is the clock trigger input to the CTC, right? 1, 2, 3, 4, 5, 6, right? But this down here is synchronized to phi. This here is not. So is this okay? Well, in the long run, it's the same frequency, okay? This signal here is phase locked or synchronized to phi. It is not synchronized to this one at all. The edges are not, we can say. But the frequency here will be the same as the frequency there, provided that this is true. Okay? As this thing speeds up, this is going to go wonky. All right. So the CTC spec specifically requires you to keep this under half of the frequency of this. All right. So how does this matter? Why do we care about all this? Well, when we're dealing with the value that comes out of Z80 over here, what'll happen is it'll run at a certain rate, but every now and then there'll be an extra pulse or an extra gap between two pulses that come out of that signal over there, because it's going to be based on this. All right. If we wanted to add the ZCTO output to this graph, so every time this thing pulses is when the main counter will reach 0. Okay. Now we don't know what the counter is. I didn't label it in here, but it will count at the rate that we see based on Q1 here when we're in counter mode. In other words, every time there's a leading edge here, the down counter will tick 1 down, right? So it'll tick there, it'll tick there, it'll tick here, and so on. So let's say we're in, we have the time constant value here. Let's say we put a 2 in here, okay? So the frequency here is divided by 2 when it comes out over there, right? So, well, let's just assume it starts with 2 here, right? So let's say we have 2 in our counter. I'll just use it in this green line here, right? There's an edge there on Q1, which comes from here, right? Q1, when we're in counter mode, is what causes this to tick down. Rising edge, he goes to a 1. Rising edge here, he goes to a 0, right? When he goes to a 0, this is going to tick up once, right? Now, if you look deep in the sheet and you look at the timing diagrams, what happens is it goes high on a leading edge of phi, plus some propagation delay. And it then goes low on the following trailing edge. So it's 1.5 periods long. It'll look like that. Okay. Now, when is loaded with 2, or 0. Once it gets to 0, it gets reloaded to 2. All right. So we end up with an edge here. This will cause it to go to 1, and this will cause it to go back to 0 again over there. And there'll be another pulse that comes out of here over there. And then it'll last for 1.5 periods, and it'll go low back over here. And then what do we got here? It gets reloaded with a 2, then it goes to a 1, then it goes to a 0 again. And there'll be another pulse here that will last a little bit longer than the sheet allows us to here. So what we got here is, notice that there's a big space between these two pulses coming out of the Z80, and then there's a shorter one here. All right. Presumably, when this was set to a 2, there would have been a pulse, there would have been 0 that caused this one to be loaded with 2 there. So there would have been a pulse just about over here. So there would be a pulse, and then a near pulse, and then another one far away, and so on. On average, this will be okay. But the point is, it jitters. Why does it jitter? It jitters because this frequency here is not perfectly phase locked to the system clock up here. Okay? As long as that's the case, which is 100% of the time, if these two come from different oscillators. They're in different, what we call time domains, that have they don't originate in the same place. They can't be. Even if I bought 2 10 megahertz oscillators with the highest precision, best money can buy, they won't run at the same speed. They'll have a tendency to speed up and slow down a little bit over time with temperature and everything else. They won't run at a constant speed. They won't even run at 10 megahertz. One might be faster, one might be slower, and the same thing would ultimately happen. Okay? So what's the bottom line? Well, the bottom line is that we're using this as our bit rate clock, and it's not going to run at a perfectly constant rate. Sometimes the gap between two of these pulses is shorter than other times. However, it'll turn out that the gap, or the difference between the longer period between pulses and the shorter one, will be no more than 1 period of phi. And as long as that holds true, we're talking about 100 nanoseconds of jitter in a signal that's pulsing at, even if you're running at 9600 baud times, 16, right? That's 100 nano, and whatever that's, or 9600, well, times 10 would be 96,000 plus half again as much, 150 some odd kilohertz, right? That's not anywhere near 10 million, right? So 1/10 millionth of a second of jitter is what you're going to see on this signal here. Now we can see that on a scope if we look really close. So here's a picture of the ZCTO output coming from the CTC. It's triggered right here. This little blue marker there shows me a rising edge. Here is the trigger. Here's one of the pulses from the Z80. The next one is over here, and I put the cursors out here. It doesn't look like they're perfectly aligned, but it's approximately 307.201 kilohertz. This is the scope measuring the frequency of the signal without any regard to the cursors. Okay, that's what this number is here. And 307.200 is exactly the correct frequency for 19,200 bits per second times 16 gives you that number up there. This is off by 1 cycle per second, which is probably caused by the jitter that you can see taking place in here. The cursors are spaced here, representing the correct frequency. What do we got here? I guess at this resolution, this number here is rounded up slightly. The point is that this cursor here is between the leading edge of the 1 cycle here as we zoom in, and we can then see, right? So this cursor is between the leading edge of this signal here and the one that comes after it over there. So it turns out that if you walk through the waves and you think about it for 10 minutes, it'll become obvious that in order for this to maintain the proper frequency, occasionally some of them will be a little bit long, some of them will be a little bit short, and it'll jitter back and forth like this. You can see the next one jittering over here, okay? Now, if we zoom in closer on this, what we have here, I put the cursors up right on the two leading edges. You can see the delta in the X dimension is 100 nano, which is exactly 10 megahertz, which is exactly the frequency of phi on the board that I'm running this particular test on. So the jitter is, in fact, 100 nanos for the reasons we already discussed, okay? Now, I went on about the jitter for long enough. I think we all get it. The point is you need to understand that it's there, number one. You need to understand whether or not it is a problem in your particular application. Now remember, I'm talking about jitter. I'm not talking about frequency error. If the frequency was off by a significant amount, your bit rate would just be wrong, and the sender and receiver couldn't handle it. In fact, it's generally accepted that about a 2.5% error is as bad as you can get with an RS-232 type communication and still be okay, be legible on the other end, okay? If you look at a 100 nanosecond error that is fixed, because remember, that's the period of phi, which doesn't have anything to do with the CTC's, bit rate clock input and the divider and all that other fun stuff. The jitter will always be 100 nano if you have an input that you're using to tick your timer that is not phase locked to phi. It will jitter at 100 nano, okay? My point there is if 100 nano becomes a significant percentage of error, at like if you run it at 115, 200 baud, this is on the order of 18% jitter, okay? You could probably get away with that. In jitter, you certainly couldn't get away with it if the frequency was off by 18-20%. But, you're pushing it, okay? So just be aware of this. The other thing that you want to be aware of when you look at this on a scope is the fact that the CTC doesn't generate a wave that's got a 50-50 duty cycle. You might, if you're not really thinking about what's going on here, you might think this goes up for 50% of the time, down for 50% of the time, up for 50%, and so on. No, that's not how it works. Remember, the zero count timeout signal is true when the timer equals 0, and then it slams back down here, okay? So it's 0 here, and it's not 0 all the other times when it's counting. It goes up when it's 0, it goes down when it's counting, and so on. All right, you read the documentation for the SIO, it's specifically designed to tolerate this type of clock input for its data rate. Okay, and that's these two chips are designed to be paired together. The CTC SIO, as documented, they're designed to be used together. All right. In other words, if you're going to use this with the CTC, or rather the SIO is going to use the leading edge on these clocks to determine when to do its internal state machine processing to handle the data transfer on its serial lines. Other UARTs might require a 50% duty cycle wave. They may, in other words, use both edges of the clock. All right, so be careful what you use. Read your data sheets. Always know what's going on. Now, unfortunately, I'm a great example of how many errors you can make, even if you're data sheet paranoid to the point where you notice subtle things like somebody misnaming one of the parameters or something, okay? It always slips by. You make mistakes. Just accept that as a part of being in this kind of business. It's one of the little games we like to play, I suppose. Figure out how to fix this when you're given the wrong information. Now, to that end, let's make sure that we all understand exactly how I've configured my retro board. All right, here's a picture of mine. Arguably, maybe perhaps this is sideways, but this, for some reason, was trying to get rid of the glare on these two oscillator cans. So let's look very closely at how I've jumpered this board and what oscillators are running at what speed. So if we zoom in really close, this here is X2. And it's running at 1.8432 megahertz, right? This is only used to go into the CTC over here and this header here that has to be jumpered correctly. We'll get there in a minute. The other oscillator here is clocking at 10 megahertz. This is X1, which is the main system clock, that's phi. So I'm running at 10 megahertz for the system clock and 1.8432 megahertz for my bitrate clock. My jumpers are set according right here. These two jumpers are set, these 3 pins in a row here, represent how you want to send the bit rate clock to the SIO chip, which is this one right here. Do we want to send the clock directly from the X2? If you look at a bit of an angle here underneath the end of this chip hanging out, this says X2 here and it says CTC over there. You can see an A and a B here. So it says SIO clock source. Where do you want to get it from? You want to get it directly from X2? You put the header shunting this pin here to the one up there. Okay, the pin 1 side of this 2x3 header. Okay, if you want to send the clock from the CTC, you hump the middle pin down into the pin that's down here. For SIO port A, you use this header here, and SIO port B, you use this one up here. Okay, so I have both SIO ports A and B set to take their receive and transmit data clock signals from the CTC. All right. Now, somebody posted me a note the other day, an early builder of this thing, couldn't figure out why they weren't getting any data, and then they figured out eventually that they needed to put jumpers over here as well. Well, let's talk about these jumpers for a minute. This is a feature. If you do not put these jumpers in, the cable here, which goes to a DB9, will not be connected to your board. They'll be floating. These are a requirement, okay? They're not optional. The same can be said about the jumpers up here for this clock. You must have a jumper either connecting these two pins up here or, as shown, these two pins down here for each of the two channels. Otherwise, there's no clock going to the SIO. If you don't put any if you don't put any jumpers down here, on this jumper here or this one down here, then you don't have any of the data lines connected from this serial cable into the retro board. Okay, so I designed this specifically so that you either put the two jumpers up in the higher position as shown here or in the lower position as shown down here, depending on which pins of 2 or 3 have the receive and transmit data signals. All right. Anyone who's done this for back in the day knows perfectly well that you never, ever have the right cables, and your pins 2 and 3 are never where you want them. So I just gave up from the beginning and said, I don't care what cables you have. You either put the jumpers as shown here or down here. The moving them back and forth changes whether the transmit signal is on pin 2 or 3. As shown here, you can see RX3TX underneath this chip. Down here, it says 2 for this pin here. They're both labeled the same. So underneath this chip that's blocking your view here, you can see that there's a 2 labeled for this pin here, and this pin here is labeled as one down here is for receive. Okay, so the idea is that pin 2 here represents which pin on the DB9 is going to be connected to either the receive signal as shown here when the jumper's down like that, or it's connected to the transmit signal when it's up like this one is here. Same thing is true for pin 3. It can be jumpered to either go to the receive signal in the retro board, or if you move this jumper to connect these two pins like I have down here, then pin 3 on the DB9 will be connected to the transmit signal from the SIO. Notice that receive from the SIO is hooked both to this pin way over here as well as the one way down here, okay, as you can see them marking down here. Therefore, you can't take the jumpers and hook both transmit and receive to the same 2 pins, right? Only one pin will be transmit and one pin will be receive based on the physical orientation of the headers and stuff like that, all right? So you need to put headers in here. You need to put 2, and you're going to either do it like this up here or this down here. If you put it together and you can't see any output, yank them out and move them over, okay? You're not going to break anything if they're in the wrong position. Don't leave it there forever, but RS-232 is robust enough, it's resilient enough that it's okay to have these backwards. You're not going to blow up anything. So anyway, this is a feature. That way you're always able to just reach in here and fix it when you've got the wrong kind of cable or adapter, or the gender's wrong, or the bits are reversed, the null modem, blah, blah, all that crap goes away. Just hook up pins 2 and 3. Pick which way you want them to go based on these jumpers. Now, I'm sure I mentioned that early on when we were looking at the schematic, perhaps long forgotten. That's what this is about in here, right? So you see these two connectors. These are the two headers, the console and the auxiliary, and you see J1 and J8 here. And if you look closely, these map to pins 2 and 3 in the DB9. Be very careful. The pin numbering of a 2x5 header is different than the pin numbering on a DB9, but these are specifically connected so that if you put a ribbon cable on this header, like I've done here, and you crimp an IDC DB9 on the other end, then pins 2 and 3 on the DB9 will be connected to pins 3 and 5 on this header here. Anyway, these two pins run into these header pins over here, and this is why you can jumper pin 4 on J1 over to 5, or you can jump it down to 3, and the same thing with pin 2 can go to 3 or 1, and so on, okay? That's what this is all about. The baud rate select jumper is this one up here. A little recap on that is these middle pins 3 and 4 go directly to the SIO chip for port B and port A. Okay, port A being the console, port B, I called it the auxiliary port. You can use that for whatever you want. Now, if they're jumpered on one way, as I said, here's X2, right? X2, your 1.8432 megahertz oscillator can be connected from pin 2 over to the clock directly into the SIO, in which case if you use this oscillator right here and you select divide by 16 in the SIO configuration, will be running at 115/200 baud. If you jumper it from 4 to 6, you're taking the data that represents the clock from the CTC, and you'll generate the little spikies, possibly with some jitter that we talked about earlier, and sending that over to the SIO. You can do port A and port B independently. And with that, you know how I set up this board so that you can make sense of the software in case it's not working for you. And here we find I reassembled my retro board with the flash programmer on it, and here's the Raspberry Pi that I use to run the flash programmer. I'm in the test directory of the main Z80 Retro board project from GitHub, and in here is where we have all the test programs for that board. So let's talk about the CTC version 1 source code here. A little doc at the top says test progi for the CTC with support for the SIO. I'm assuming the SIO will be running in pulled mode. That's what we talked about before. And you're supposed to use J11A to select between 115.2 and 19.2 when you're running the code in this example program. Now, as you can see, we have the usual beginning. We include io.asm, where we have the equates that allow me to put symbolic names on the various I/O ports and things like that. We set the stack top to 0 because it's going to wrap around into the end of memory. We talked about all that before. We copy the flash into the static RAM here. We beat that one quite dead by now. We load the stack pointer with the stack top, and we go on to our merry way to run our little test program. So what do? Now, I've put some comments in here that have all the divisors for the various baud rates that we can support given the board the way I've configured it, okay? The comment here says that all these numbers down here assume that we've set SIO up in divide by 16 mode. As you might remember, we can choose a different divisor in the SIO, like 16 versus 32 and 64 and stuff like that, okay? So in order for this to work, we assume that the crystal is running at 1.84 whatever megahertz. We're dividing by 16 in the SIOA for its clock, and we're going to use register C. Ultimately, you're going to see this is the value we're going to put in the timer counter register that is the divisor that we're going to use on the input baud rate clock, okay? So if we take 1.84 some odd megahertz divided by 6, we're going to get 19.2 times 16 coming out of that CTC, all right? So what do? We load C with some divisor. We call initialize CTC1 because that's going to initialize channel number 1 on the CTC. We've already talked about the SIO code, and this is the exact same code, not changed in any way. We already talked about printing characters from the B register and so on. So we're going to print out a character, turn in a line feed in order to get the cursor to the left side of the screen. So I don't have, if it's left in the middle of the screen and I don't want to screw up the output of this program run, I'm going to do a hex dump of the code. We've seen that before. Then I'm going to fall through into this loop here, and I'm going to run the usual echo loop that we've seen before as well. So this thing really is the exact same thing as the regular old SIO echo application that we've already talked about, except before we run the echo loop and initialize the SIO, I'm going to initialize CTC1, okay? And I'm going to tell it what to divide the baud rate clock by, all right? So here's my initialization for the CTC1. The CTC is very simple. All we need to do is set some bits to tell it what mode we want it to be in, tell it what we want to use for the divisor, and we're done. That's all you got to do, okay? Now, how do you figure out that that's all you got to do? You get to read a 200-page manual. So let's focus right in on what I'm doing here with these two settings, okay? The comments over here, I double-checked them. I believe they're correct. This one runs it in counter mode. This one over here will run it in timer mode. Okay? This one's not useful because of what we discussed earlier. We can't get a clean divisor to come out of this thing in timer mode unless you put an oscillator in the X1 socket on the board that has a frequency that is convenient for generating bit rates. And by the way, that's a very common thing to do back in these days because these oscillators cost a lot of money, relatively speaking. Okay? So it was not uncommon to run your Z80 at some wonky speed because it was convenient to be able to use the same oscillator or crystal, if you built the oscillator yourself, as the serial data rate divisors were needed. Okay? So I give the option to do that or not to do it, okay? So you have both choices here. Honestly, my original version 1 of this design used a single oscillator that ran at like 9 point some odd megahertz, which is almost 10 megahertz anyway. I mean, performance-wise, it would have made no difference. But the problem is I couldn't get the oscillator they were out of stock. So, I couldn't find one. So I just said, forget it. I'll just use two separate cans, and then we all have the option to go either way. My point is, if you do not populate X2, the baud rate clock oscillator, you can use the same oscillator that's hooked up to the Z80 and just let it free run off of that if you run it in timer mode. So let's look closely at what it means to configure these two modes with the various settings. The only difference here, as you can see, is a single bit is on or off depending on whether we want to use the baud rate input to the CTC or we want to use the phi clock, all right, on the CTC, right? So let's look at the manual and figure out what it means to put a 5, 7, and hex into the CTC1 port. Now, I guess it would be cruel of me not to remind you of what the heck CTC1 and CTC2 and so on is all about. Here's the schematic. Realize that A0 here is connected to CS0 and A1 is connected up to CS1. These two bits allow you to select which register you want to talk to inside the CTC. There's 4 registers, one for each of the 4 channels, okay? And those registers are used to set both the mode and the timer constant value, the divisor number. All right, so let's go back to our user guide from 30 years ago and have a look-see at this particular page here, which is correct, okay? We have 4 channels. They're numbered 0, 1, 2, and 3. And it says if the CS0 and CS1 bits that we were just looking at, just talking about, are set to both 0, I'm talking to channel 0. If I got a 0, 1 on the 2 bits, I'm talking to channel 1, 2, and 3, and so on, all right? And the control register looks like this. Nice diagram, all fits on one page, easy to read, okay? Now, let's say you don't like reading old crappy manuals and you want to read the new one. Matters of the small things and matters of the big things. Someone decided that they know better than the entire rest of the universe, and they numbered these columns wrong. This, again, is our wonderful user guide from the art department rather than from the engineering department. This diagram is completely wrong. Channel 1 is when there's a 0 on CS1 and a 1 on CS0. As clearly drawn in this diagram on this page in this manual, which is correct. So basically they reverse these headings, okay? You know, is this the end of the world? No. Presumably you'd figure this out eventually, but you trip over enough rakes and you have to just get them out of the lawn, people, all right? Again, this manual does leave a bit to be desired. I talk about it, though, because there's some stuff in here that may be more useful to you. This is the equivalent picture that we saw on the scanned-in manual as well, in more tabular form, that wants to use much more screen real estate, but, ooh, the font is nice and I can copy and paste out of it. You know, this is nicer, but it's whatever. At least this diagram here appears to be correct to me when we compare it back to the diagram in this manual here. But I like this better because I think this one diagram is easier to read. It's more succinct. It fits on one page. If I can get my scroll bars and things to do the right thing here. And we can see everything all at once. You got the left to right orientation as well as the detailed description. You don't have to go back and forth between two separate tables. So I'm going to use this, okay? What are we looking at here? We got control or vector. Now, we're not going to talk about interrupts in this particular discussion. The value 0 means that the data that's loaded into this control register is going to represent an interrupt vector, okay? Versus the control word, okay? The control word is what all these things are used for that we're looking at here. In this discussion, we're not going to program the vector. Okay, we're not going to use interrupts in this discussion. I think I've gone on long enough. We'll do interrupts in some other time. You can set 1 in this bit position here to reset the CTC. If you put a 1 in this position here at D2, it means that the next value that you write into this register will be the time constant. That's your divisor. Down here, notice there's an asterisk over here. This is the timer trigger. Okay, if you're going to operate in timer mode, and remember, we're going to operate in counter mode. This allows you to determine when exactly the counter starts running. If you're in timer mode, do you want it to start running right away as soon as I put the constant into the constant register? Or do I want to wait until the clock and trigger pulse arrives? Okay, so this is application dependent, really. Okay, if you're going to just use a free running timer, you want to generate interrupts to let you know the time of day clock or something like that, you want to have a 0 in here. Okay, if you want to do a more advanced application to measure the widths of pulses or something, then you might put a 1 down here. Okay, we're going to use a 0. And for the bit rate, we're not going to use a timer at all, so it really doesn't even matter. What happens over here? The trigger edge selection. Do you want the rising edge or the falling edge of the clock input to determine whether the point at which the timer advances? I prefer to use rising edges because I always think of that in that way, so I'm going to set this thing to a 1. Doesn't really matter. You just have to pick one. Do you want a prescale 256 or 16? This is the choice that I showed you. You'll notice the asterisk on there. It only applies to timer mode. We don't care when we're dealing with a bit rate clock, so we can just set it to 0 or whatever. It doesn't matter. Now, do we want to operate in timer mode or counter mode? That's what this bit here is for, okay? And you'll see this is the only bit that's different in the example code that I showed you a minute ago, which I believe set the register to either 5-7 or 1-7, okay? Which is the only difference is that this bit here would change, okay? And the last bit here is whether or not you want the CTC to try to generate an interrupt signal to the CPU every time it gets to 0. We're not using interrupts, so I'm going to disable them in the CTC, and I'm going to store that as a 0. All right, so this is pretty much everything we need to deal with, and the understanding of the hand-drawn diagram I gave you before. Now, notice it says no time constant follows or time constant follows. The idea is that if this is set to 1 when you write in a control word, you're supposed to write in another byte immediately after that the CTC will use as the time constant for the channel that you're programming, okay? And that's exactly what the code does that I showed you a second ago. All right, so we put a 57 in there. That's the 5 represents bits 4 and 6, and the 7 represents bits 0, 1, and 2. So we got a 1, 1, 1 down here, right? We got a time constant to follow. We want to reset the channel. And we got a 1 in here, which means I want to write a control word, and I'm not messing with interrupt vectors. Okay, that's the 7. This is a 0. Doesn't matter because it's timer mode only. Now, we have a 5 over here, the most significant 4 bits. That's a D4 and a D6 are on. So I got no interrupt. I got a 1 here for counter mode. Doesn't matter, but I got a 0 here for this, and I got a 1 here for the rising edge, just as I said a minute ago. So there's my 57 into CTC1, and I've got, then I put the value in the C register into the accumulator because I cannot output C. I have to output A because it's the limitation of the Z80 machine language. So I'm going to put the value in A, which is the divisor, which I think was set to 6 above, right? Let's see here. Where are we? Yeah, if I divide the clock by 6, that's what I want to do, and I'm returning out of here. So this is everything that we need to do to just simply set up a divide by 6 counter on the CTC so that the frequency that's headed over to the SIO will be 19.2 times 16. So if we take 19,200 and we multiply that by 16, we end up with this. This is the target frequency that we want to get out of the timer. And as you saw on the scope a minute ago, that is the frequency that my oscilloscope said was coming out of the CTC. And if we go back to the schematic again, remember we got 1.4, what do we got? 18432. Okay, so that's 1843200 hertz, right? Divided by 6 should equal this number up here. We see we got the same exact thing. That's exactly what we want. So this should be the frequency coming out of the CTC, and we should be able to be running in 19.2. I always do a make world. I always make a world target in my make files that always does a clean and a full rebuild in case I screwed up the dependencies. It works great, especially on a trivial project like this, where I can recompile, reassemble, a dozen programs in less than a second. Just forcibly recompile everything, and you're always going to be fine. So we want to reprogram that using the command in the README file, which is up here. We've seen this many times, right? So we want to reprogram this binary file right there. When we do that, it's going to reset our CPU, and we set it to run at 19.2. Now I'm in Minicom, and if you don't know how to use Minicom, you hit Control A and then you hit Z. That's a little help thingy over here. It opens up this menu, and if you hit P right here, you can change the parameters. You see that A and B say previous and next, and if I hit A, the bit rate's going to change around. I hit B, 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 it goes backwards the other way, all right? So cycle it around until you get 19.2, 8, none, 1. If you got the wrong bits, hit V to go into 8. You want no parity, you would hit L, and so on. I think you can figure that out, I hope. And 1, of course, is the number of stop bits. You can hit W down here to select how many you want. Or I guess you could just hit Q like this and just set the whole thing to 8, none, 1, because this is an incredibly common thing, as is 7, even 1, so they've just put shortcuts in there for that, all right? So the point is I'm running at 19.2, so let's go ahead and run the programmer. And we see the hex dump being printed at 119.2. Okay, so this is exactly what we want it to do, and it does in fact work. So let's go ahead and rerun this editor and play around with this a little bit. So let's just, for fun, run it at 115.2 by doing a divide by 1. We'll have a look-see at the jitter that's going to be caused in here, all right? Now remember, at 115.2, we want the data to flow right through the CTC because it has to run at 1.8432 megahertz. But due to the synchronizer, this is going to get a lot of jitter put on it. So let's go ahead and program this thing up and rerun our Flash programmer. Let's bring in the terminal. Control AZ. Let's go back to P and get back to 115.2, which we got a shortcut for E. Hit enter, and let's see what happens with 20%, on the order of 20% of jitter. Will it work? I think the answer is yes. It does work, okay? We got a 20% jitter, and we're still flying. Let's look at the oscilloscope and have a look-see at just how bad this really is. And keep in mind, this is jitter, not frequency error. And the takeaway here is just how robust RS-232 really is in the face of jitter. And the reason it works is because of the accuracy that's obtained when you have this divide by 16 clock that we talked about before when we were talking about the SIO chip. By running the clock faster than it needs to be and then dividing it down in the SIO and then taking 7 ticks into the first start bit and finding the middle of that bit time and judging the position of all the future ones based on that one, it can overcome this kind of jitter. That's what it's for. That and the 2.5% maximum error that it can tolerate if the frequency is wrong. Okay? Now we have a good frequency, but we have a lot of jitter, and you just saw it right here. It looks pretty good. And with that, I think we pretty much can wrap this. I'm going to leave the timer mode variant of this as a test for the viewer. Feel free to play around. You can even just take X2 out and stick it in X1, run your whole Z80 at 1.8432 megahertz. It'll go slower, but you will then have a phi clock that's running at 1.8432, and you can run that through the CTC in timer mode if you want. Keep aware of, though, that in timer mode you have to use one of the prescalers. So it's going to divide your speed down by 16. So your maximum bit rate, if you use that as your oscillator, will be limited to, I don't know, 9600 baud or even less for the top speed with that size crystal. But it's still an achievable thing to do if you want. So thanks for watching. I'll see you next time.